Thank you for having us. I'm very glad that, yeah, in the next 10, 15 minutes, yeah, I would like to share my lessons learned on regarding how and why we are using two types of simulation tools. And but we wouldn't be going into the technical detail, unfortunately, today. But still, hopefully, I can give you a new perspective in terms of how to see simulation from the software lens. So we advocate for a paradigm shift of using simulation for shifting left and then continuous testing for functional software verification on RISC-V systems. And our approach is to combine both emulation and simulation using QEMU for fast unit-based emulation, as well as Intel Simix for product level of simulation. So that I'm happy to learn from you guys this workshop that I'm not alone in this thinking. Yeah, the front grade TSIM3, the Renodes, the TCL, Pascal from DLR somewhere. Yes. So we should talk more. Yeah, shared similar kind of thinking. So ultimately, we want to embrace change early with our RISC-V design so that we can find an effective way to develop space software solution. So before joining the dark side, I've become the product manager, look after system simulation. I trained as the embedded software engineer in the UK. So I like coding and I like the shiny tech things. And thanks to Thales, yeah, I work on multiple real-life programs that have my software actually still in operation in the field, underwater, in the air, and in orbit. So the most important lessons that I've learned is not about the size of the code, how many lines that are right in my product, but more about how we test, how we design for change. So knowing that we are going to develop some software that is going to stand the test of time. And within the embedded and space sector, RISC-V architecture actually give us significant opportunity as well as challenges because its defining characteristic is very extensible, is very customizable. The freedom that give us through using unique instruction and configuration parameters are both very exciting and terrifying. So it raised the question, therefore, as a software developer, how we can embrace and to make sure the reliability of a mission-critical software can be developed in such a flexible and potentially changing hardware platform. And this question actually perceived as a risk, in my mind. And initially, we see it as a significant risk. Perhaps RISC-V project is risk times 5 times. So it's very risky. So, and at the same time, there's also pressure for shorter development cycle and cut costs, and there's all sorts of different tensions that we need to develop faster and maintain reliability. So traditional waterfall, testing at the very late cycle is just not satisfy this need anymore now. It is also Win-Reverse DNA to support customer building mission critical software. So it's fun fact, I found out is that more people know about our flagship product, RISC-V, than our company's name. So RISC-V have actually got, well, it used to have 100% outsourced market domination in Mars, but not on Earth yet. So it powers the rover, it powers many satellites. So our tests and our code base actually have a ratio of size of one line of code have 100 lines of test code in order to exercise that. So I just want to give you a perspective that we are very serious in terms of software testing. We spend a lot of time, we spend a lot of effort, and we spend a lot of investment. I share this from our view, simulation is not a hardware replacement. And this is from our perspective. Simulation is just a representative platform so that we can run, we can experiment, and we can test software in works. It captures what we know about the target hardware, very similar to a weather model that we have to forecast weather. It captures our know-how about the weather system so that we can make better forecasts. So therefore, we use the model as a runtime with runtime constraint so that from the software developer point of view, we have got the advantage that we have the freedom now to relax the constraint in early on in the design cycle so that we can increase the number of CPU core, we can increase the number of memory, we can remove component that doesn't help us in developing the software. And then we can, as the project progress, we can start tightening that the constraint, make more peripheral available, make a higher fidelity of model and incorporate into the design so that we can test and mature our design and understand the performance. So this diagram, I just want to point out one thing is virtual hardware is only one part of the system simulation. We actually encapsulate from our perspective, we learn it's much better to encapsulate as well as the operating system, the hypervisor, together with the virtual hardware. So this is our view of what actually system simulation means. There are quite a lot of reasons that system simulation help us to do. So, and from my perspective, the biggest gain that we have for simulation is about collaboration, is to help the team to share one common know-how and knowledge of the system. We use emulation for unit-based testing. It uses the binary compatible instruction set. It's very fast to run. Yes, it's very high level. And then we have got the next level of simulation to use for product-based simulation that allowed us to bring up multiple targets at the same time, which is much more higher fidelity. And then we're combining both emulation and simulation in our workflow so that we can inject fault, inject data so that we can make data-driven decision. Yeah, this is an example that we use QEMU. Actually, in the paper that I submit, we actually have managed to run QEMU on the browser so that the developer don't even need to install QEMU. They don't even need to know how to launch QEMU. They just go onto the browser and then run their unit tests. And from a CIMIC's point of view, there's a lot more setup. However, this gives you the flexibility of simulating multiple targets at the same time, as well as creating checkpoints and fault injection. What we have learned is about collaboration, helping the team to share the tools, to share the know-how. Some data that we have collected from our usage as well as our customers' usage as well. I think the one that two things that I want to point out. We actually have data point from our customer telling us that after adopting simulation, it helps them to shift left their design by, on one project, 69 days, another project on 220 days, as well as because the simulation can run on hyper simulation, which means that you can run faster than real time. So some 2 years of test cases can be completed in 3 days. Change is the only constant, as some wise people said before. And in conclusion, proactively embracing and evolving the RISC-V landscape by employing some robust methodology can help us to mitigate the complexity effectively. So it helps us to transform our RISC-V risky project to a RISC-Fine solution for everyone. So everyone is good and happy about our RISC-Fine solution. And last but not least, if you're interested to try it out, actually you can check out our documentation site. We also got a GitHub account. There's a free, open CIMIC's public version that you can download, and there's a Winriver lab that already contains some RISC-V target that you can start using. So happy software coding. All right, thank you.